So cosmology has seen this profound transformation over the last half century, which is, it used to be a very speculative subject, and it's completely transformed, and I've been lucky to witness that. So there's a real interest and impetus to try and look for new physics, and that is physics which isn't described by the standard model of electromagnetic, weak and strong forces and general relativity. One of the drivers for looking for new physics is we're up against these three big puzzles that come from cosmology. The first puzzle is we don't really understand how the universe began or evolved at the beginning, even though we can kind of map out what, vestiges of what the universe was like in early times. And we have a theory of how that might have happened. It's a theory which is known as the theory of inflation. We don't really have a model which we are sure is how it happened. The second puzzle is when we look at how galaxies behave. They shouldn't behave as they do. Galaxies, if you just let them evolve under the normal forces and gravity, would fall apart. You need something holding them together. And the thing that holds them together, we now call dark matter. We believe there's some kind of stuff which has much more mass than normal atoms, the stuff that we work with, which keeps galaxies together, but which doesn't emit light, so we don't see it. The only way we see it is the way that it gravitationally affects things. The final puzzle, which is a really striking puzzle, is that the universe, which we know is expanding, seems to be expanding in an unexpected way. Instead of slowing down in its expansion, which is what you'd expect because of the gravitational pull of things, it seems to be accelerating. Again, we speculate and we believe that this is driven by something called dark energy. It's something that has very exotic properties, which instead of pulling, pushes. And we've really made no progress on figuring out why this has happened. We don't know what drives inflation. We don't know what the dark matter is, and we don't know what the dark energy is. So we have this dichotomy of this science that has become precise and rigorous and incredibly powerful on the one hand. On the other hand, we have these questions which remain unanswered. So there's many ways in which we can try and address this, what I call cosmological chasm. First of all, there are different theoretical approaches. One is that we hunker down and we think, we've built this theory of the fundamental forces, which has worked incredibly well, and at its root have been mathematical principles. And so we should just pursue mathematical consistency, mathematical principles, and just go as far as we can, just building the best, most beautiful, most elegant mathematical structure. And the hope is that out of that will kind of tumble an explanation for dark matter, dark energy in the beginning of the universe. That pursuing mathematical elegance and consistency will give us the answers to the universe. It's far-fetched, but it's worked in the past. Arguably it worked with Einstein discovering the general theory of relativity, and it's kind of been the guiding principle behind a lot of theoretical physics. Another approach is that you're up close to the data, right? And what you do is you build what are known as phenomenological models. You think, okay, I'm going to come up with a simple mathematical model that explains this aspect, and then I'm going to look at what it does and why it behaves the way it does, and then I'm going to see how it relates to the rest of physics, and if it breaks stuff that we already know, if it fits in, and let that guide us to the answer to what are these things, what is dark matter, what is dark energy. And it's kind of a dangerous approach, this phenomenological approach, because you may end up breaking things that you know are true, and so then how do you reconcile them? We're accumulating a huge amount of data about the universe, where, when we do these particle collisions, when we monitor gravitational waves, when we map out the universe using telescopes and map out billions of galaxies. But maybe we should revisit this data and look at this data in a new way. One example is we often look at how galaxies organize themselves with regards to each other and try to infer something about how the universe is expanding and how the gravitational force works. But maybe we should look at galaxies themselves and start to look inside galaxies and see if we can look for any evidence from new physics by the way that galaxies themselves are built up. It's a kind of a ludicrous proposal because galaxies are very messy systems. They're not only gravity plays a role, but other things play a role. So often people will look at them and say, no, they're too messy. But we have so many images of these galaxies, and they're going to be so precise, these images, that maybe we should just bite the bullet and look at them and try and delve into them and try to disentangle the mess from something interesting. The other approach, I think, is to go back and, instead of building huge experiments, think about tabletop experiments, loosely speaking. Our knowledge of the quantum and of technology has progressed dramatically. And can we harness the, quantum technologies to let us learn about fundamental physics? Can we build interesting, different experiments? For example, one thing that people are excited about is instead of doing interferometry, interference with light rays, you start doing interferometry with atoms. Can we do something like that and start to probe, look for new forces, look for the effects of new forces or new particles by using smaller experiments, but which are just different, new technologies? The thing that concerns me most, it's this dawning realization that we may never solve these fundamental problems. We may never bridge the cosmic chasm. We build these incredibly precise instruments or observatories. We build particle accelerators, we build telescopes, we build gravitational wave detectors, and they've taken us a long way. And a sensible philosophy is, okay, these have taken us a long way. We should pursue this. We should just push more by building bigger and better. And it's quite possible that by doing this, by building more powerful particle accelerators, building better telescopes and building better observatories, that we will learn more about dark energy and dark matter, or how the universe began. And we might pass some kind of threshold of discovery where we realize, aha, it's this. But that might not happen. What might happen is we will get to know that there is dark energy, there is dark matter, and the universe behaved in a certain way at early times better and better, but that's it. We won't find out what actually happened or what it actually is. And I think that's the real worry of pursuing what has been a very successful strategy. There's a worry that we will increase the precision of our ignorance without actually flipping over into knowing something new.